The Boeing X-40A was an experimental spacecraft developed to test technologies for the future of reusable space vehicles. Designed under NASA's X-Vehicle program, it explored precision reentry, autonomous flight, and recovery techniques. The X-40A represented a stepping stone toward vehicles like the X-37B and modern reusable spacecraft. Its flights were brief but pivotal, revealing the challenges and promise of next-generation space technology. Built for testing, not for orbit, the X-40A carried no crew or payload, yet its lessons were invaluable. Engineers pushed it to the limits of autonomous flight and hypersonic reentry. Every mission provided data critical to shaping the future of reusable spaceplanes. In this documentary, we uncover the story of the X-40A, its design, flights, and lasting impact on space exploration. The X-40A program began in the late 1990s as part of NASA's effort to develop reusable spacecraft. Boeing was tasked with creating a subscale prototype capable of simulating orbital reentry dynamics. The goal was to validate autonomous flight, guidance systems, and landing techniques for future vehicles. Engineers focused on aerodynamics, thermal protection, and structural durability. The project reflected the growing interest in reusable spacecraft to reduce cost and risk. The vehicle featured a blunt nose and delta-wing design, optimized for atmospheric reentry. Its small size allowed testing without the expense of a full-scale spacecraft. Advanced flight computers controlled every maneuver, simulating conditions a crewed vehicle might encounter. Every detail was meticulously engineered to gather precise data. The X-40A was a testbed for technologies that would define future missions. Construction combined lightweight materials with heat-resistant coatings. Engineers designed it to withstand multiple test flights under extreme conditions. Sensors monitored structural loads, temperature, and flight dynamics in real time. Data acquisition systems were critical to understanding the performance of reusable designs. Each prototype represented the cutting edge of aerospace engineering. The X-40A was launched from a helicopter or drop platform to simulate initial orbital conditions. Free-flight tests allowed the team to observe aerodynamic behavior during descent. Recovery systems, including landing gear and control surfaces, were rigorously tested. Autonomous guidance systems were continuously refined based on flight results. Each mission pushed the boundaries of unmanned spacecraft testing. Testing emphasized precision landing, a key requirement for reusable vehicles. The X-40A needed to land on a runway accurately, replicating future spaceplane operations. Engineers analyzed approach angles, velocity control, and atmospheric effects. Every landing provided critical feedback for improvements. Successful tests demonstrated the viability of autonomous reentry vehicles. By the early 2000s, the X-40A had completed multiple test flights. Its performance exceeded expectations in some areas while revealing areas needing refinement. Engineers used every flight to iterate design and control systems. The program built confidence in the feasibility of reusable spaceplanes. The X-40A had proven itself as an essential stepping stone for future spacecraft. Flight testing began with simple drop tests to validate basic aerodynamics. Each flight gathered data on stability, lift, and drag during reentry conditions. Engineers evaluated control surface effectiveness at varying speeds. Even small anomalies were carefully analyzed to improve reliability. The X-40A became a critical tool for understanding hypersonic flight dynamics. As testing progressed, missions increased in complexity. The vehicle simulated full reentry trajectories, including approach and landing. Autonomous flight computers managed all maneuvers with increasing precision. Recovery systems demonstrated the ability to land safely on a runway. Every mission enhanced understanding of reusable spacecraft operations. Thermal protection systems were monitored throughout each flight. Sensors measured temperatures across the fuselage, wings, and control surfaces. Data informed the design of larger reusable spacecraft like the X-37B. Engineers refined materials and coatings to ensure survivability during extreme reentry. The X-40A became a benchmark for thermal reentry testing. The program also tested navigation and guidance under realistic conditions. GPS, inertial measurement units, and onboard sensors guided the vehicle autonomously. Accuracy was measured to ensure future vehicles could land precisely. The X-40A consistently demonstrated reliable control and stability. Its success validated autonomous spacecraft concepts. Flight crews and engineers observed how small adjustments improved overall performance. Minor tweaks to control algorithms increased landing precision. Structural behavior under dynamic loads was better understood. Each flight informed the next, creating a feedback loop of improvement. The program illustrated the importance of iterative testing. Data from the X-40A informed not only NASA but also the aerospace industry. Lessons learned influenced reusable spacecraft design worldwide. Engineers refined models for trajectory, thermal protection, and autonomous guidance. It demonstrated that small-scale prototypes could significantly reduce risk for full-scale missions. The X-40A set a precedent for methodical spacecraft testing. By the end of its flight program, the X-40A had completed all planned missions successfully. The vehicle demonstrated that autonomous reentry and runway landing were achievable. Its contributions paved the way for next-generation spaceplanes. The program proved that reusable unmanned test vehicles were both practical and essential. X-40's legacy extended far beyond its small size. The X-40's delta wing shape allowed stable flight during high-speed reentry. Its blunt nose and heat-resistant materials protected it from extreme temperatures. Engineers integrated advanced flight computers to handle autonomous maneuvers. Every system was designed to replicate conditions a full-scale reusable vehicle would face. The X-40A became a testbed for next-generation spacecraft technology. Autonomous guidance was at the heart of the program. The onboard computers processed real-time data to adjust flight paths. Sensors monitored speed, altitude, and orientation continuously. Control surfaces reacted precisely to changing aerodynamic forces. Pilots on the ground observed every maneuver for validation and improvement. The thermal protection system was a key innovation. Composite materials and heat-resistant coatings shielded critical components. Engineers measured temperature gradients to refine future designs. The data informed larger projects like the X-37B spaceplane. Every flight improved understanding of reusable spacecraft survivability. Landing precision was a central design requirement. The X-40A needed to autonomously touch down on a runway within strict tolerances. Flight tests evaluated approach angles, descent rates, and braking effectiveness. Adjustments were made in real time by onboard systems. These tests ensured confidence in future reusable space vehicles. The vehicle's small size allowed frequent and cost-effective testing. Engineers could iterate quickly, applying lessons from each flight. Sensors captured aerodynamic, thermal, and control data in minute detail. Each test refined both the airframe and software. The X-40A proved that unmanned test vehicles were invaluable. Structural durability was another major focus. The X-40A had to endure multiple high-speed flights safely. Reinforcements were applied to wings and fuselage to prevent fatigue. Engineers tracked stress patterns to ensure long-term reliability. Its robust design demonstrated the practicality of reusable spacecraft concepts. Overall, the X-40A combined aerodynamic innovation, thermal engineering, and autonomous control. It set benchmarks for future reusable spacecraft. Engineers used it to de-risk technologies for operational vehicles. The data collected influenced the design philosophy of unmanned spaceplanes. The X-40A was small but revolutionary. Flight tests pushed the X-40A to the limits of autonomous operations. It performed drop tests and glide landings with increasing precision. Engineers analyzed data to improve guidance and control. Every mission refined approach profiles and landing accuracy. The X-40A consistently demonstrated that autonomous reentry was achievable. The program also tested environmental stresses. High-speed descent generated intense heat and aerodynamic forces. Sensors monitored structural loads and temperature fluctuations. Data from these flights informed materials choices for full-scale spacecraft. Engineers learned how to mitigate risks during actual orbital reentry. Navigation and landing systems were repeatedly validated. GPS, inertial sensors, and onboard computing worked in concert. Accuracy was verified under varying wind and weather conditions. The X-40A consistently landed within designated runway zones. This validated concepts crucial for future reusable vehicles. Each test contributed to larger NASA programs. Data informed the development of the X-37B and other reusable spaceplanes. Engineers applied lessons in guidance algorithms, thermal protection, and structural integrity. Every iteration reduced risk for future missions. The X-40A became a cornerstone of autonomous spacecraft testing. The program also highlighted the importance of rapid iteration. Engineers could quickly modify systems based on flight outcomes. Each flight cycle improved confidence in hardware and software. Repeated success validated the approach of small-scale unmanned prototypes. The X-40A proved iterative testing was highly effective. Crew and ground teams gained valuable experience in managing autonomous vehicles. Operators refined procedures for launch, monitoring, and recovery. Engineers tracked performance in real time to make data-driven adjustments. This experience helped establish protocols for operational spaceplanes. The X-40A was both a vehicle and a learning platform. By the end of its test program, the X-40A had met or exceeded all its objectives. It demonstrated controlled reentry, accurate autonomous landing, and structural resilience. The program validated technologies critical to future unmanned and reusable spacecraft. Engineers celebrated the success as a stepping stone for operational missions. The X-40A's impact extended far beyond its small flights. The X-40A's legacy lies in proving that autonomous reusable spacecraft were feasible. Its tests informed the design of the X-37B and other advanced spaceplanes. Engineers applied lessons in guidance, thermal protection, and structural engineering. Every flight reduced risk for operational reusable vehicles. The X-40A became a model for efficient, data-driven spacecraft testing. Even though it never reached orbit, its influence was profound. Lessons learned shaped the development of operational unmanned vehicles. NASA and Boeing used its data to refine reentry and landing protocols. Engineers gained confidence in autonomous spacecraft systems. The X-40A's legacy continues to impact aerospace programs today. The vehicle's design innovations set new standards. Delta-wing aerodynamics, heat-resistant materials, and autonomous control combined into a practical test platform. These systems influenced the next generation of reusable spacecraft. Engineers still reference its flight data for new designs. The X-40A proved that small-scale prototypes could lead to major breakthroughs. Flight testing highlighted the potential of autonomous spaceplanes. The X-40A consistently performed landings within strict tolerances. Guidance algorithms proved reliable under dynamic conditions. Structural integrity was maintained despite repeated high-speed flights. The program validated the concept of iterative unmanned testing. Its contributions extended beyond technology to operational philosophy. Small, unmanned test vehicles became an accepted method to de-risk expensive missions. Lessons from the X-40A influenced procedural and safety standards. Recovery operations were refined for future spaceplanes. It demonstrated how incremental testing accelerates aerospace innovation. The X-40A also inspired confidence in the feasibility of reusable spacecraft. Its success showed that precise, autonomous flight was achievable. Engineers and planners used its data to support ambitious spaceplane projects. The vehicle's achievements proved small-scale testing could yield massive results. The X-40A remains a symbol of innovation in reusable spacecraft. Ultimately, the X-40A bridged the gap between concept and operational reality. It demonstrated that unmanned, reusable spaceplanes could work reliably. Its tests paved the way for the next generation of space vehicles. Every flight contributed to the knowledge base of modern aerospace engineering. The X-40A will always be remembered as a pioneering step in autonomous spaceflight.